Sandy, and we will continue discussing quantum mechanics and the quantum model for the hydrogen atom. This link will take you to an animation that will allow you to see how all of the orbitals look when they are put together. So watch it. And we're going to cover 1210, electron spin and the Pauli principle, and 1213, the Aufbau principle and the periodic table. 1211 and 1212 will be mentioned, but those are pretty brief. Still, they will be covered. One reminder and something that we need to know ahead of time before we engage in this discussion has to do with the way that the energy diagram for a hydrogen atom looks like when compared to a multi-electron atom. So on the left, we have what would be the hydrogen atom, just one electron. And one of the things we see, and we have commented, was that the orbitals for a given shell, for a given n value, principal quantum number, the orbitals are degenerate. That means they have the same energy. So we see that, for instance, for 2s and 2p, we have the same energy. We have a different value for L. L equals 0 for 2s and L equals 1 for 2p. But they have the same energy. They are degenerate. In reality, what happens when we have more than one electron is that those electrons will be interacting, will be repelling one another. So the potential energy will change, the energy of the individual electrons will change, and that is going to cause a distortion of the distribution of the orbitals in the energy diagram. And not all of the orbitals for a given n value will have the same energy. That is, they will not be degenerate. So instead of being at the same height in the energy diagram, the 2s and 2p orbitals are at a different energy. 2s are lower in energy than 2p. But still, the orbitals within a subshell are degenerate. That is, the orbitals that have the same L value will have the same energy. So 2p orbitals, the three orbitals have the same L value, and they will have the same energy. And that applies for the rest of the distribution of the orbitals. And as we see, what that causes is that the sequence going upwards, the sequence of the orbitals changes considerably when compared to the one electron model. And here we have, for example, that we go up from 2p to 3s, then 3p, but instead of coming next, instead of the 3d coming next, the next one is 4s. Okay, so the sequence changes, and just keep that in mind. We will discuss it, we will use that for our discussion later. So we're going to assume that we have a one electron atom, and our discussion will be based on that because it's the simplest scenario, and then we can build up and do something that's a little bit more complex. So drawing the energy diagrams like that would be cumbersome. It would take too much time. So we do what we like doing in sciences. We create symbols, or we create visual models to condense information. Instead of having the energy diagram, we're going to use this type of diagram that I have down here, in which each orbital, instead of being just one horizontal line, we're going to represent each orbital by using a box. So we have the 1s orbital, followed by the 2s, and then come the 3 2p orbitals, 3s, 3p, 3d, and so forth. And we're going to call that type of representation orbital diagram, which we must clearly differentiate from the energy diagram. And we could label each individual orbital to show in such a way that we show the m sub L value. So instead of just saying these are the three 2p orbitals, we could say This is the 2px, 2py, and 2pz. The same for 3p and the same for 3d. We will see why that is not indispensable. And as a reminder, again, I have here the sequence going from 3s to 3p to 3d. That is not necessarily the case. That would be expected if we had a 1 electron atom. We see that here, 3s, 3p, 3d. However, I just mentioned previous slide that sequence is not what we observe when we have more than 1 electron. In that case, there's a slight change. It goes from 3s to 3p and then to 4s and then to 3d. Okay, so keep that in mind. But we're going to use the simplest possible model for our initial discussion. So far we've said that orbitals are characterized by 3 quantum numbers that come from the solutions to the wave function. These 3 numbers are n, l, and m sub l. We also discussed what their physical meaning is and what the possible values for those numbers are. We know those rules already. And there's one thing that we will not discuss in depth, but coming from certain observations, spectroscopic observations, scientists figured out last century that the spectra were not fully explained by just using those 3 quantum numbers, n, l, and m sub l. And through the experimentation and theoretical approaches, they found out that there is another quantum number that we call the spin quantum number, and we use m sub s as the symbol. And this quantum number is a property of the electron. It is not a property of the orbital like n, l, and m sub l, but it is a property, characteristic of the electron. And understanding what that means, what the spin quantum number means, is beyond the scope of this class. So what I'm going to do is I'm going to invite you to think of the spin quantum number just as a property that emerges for very small objects, for quantum size objects. Just like we understand the mass as a property of an object, we don't question where does that mass come from, right? We just assume that's a property of an object. The electron, for instance, we're going to say that the spin quantum number is a property that is intrinsic to the electron. And this property, they figured out that can have one of 2 values, 1/2 or -1/2. And we refer to 1/2 as spin up, -1/2 spin down, and we use arrows to symbolize that. Once again, this is a property of the electron, not a property of the orbital. However, when we describe electrons, we're going to also use the properties of the orbitals. So we have 3 quantum numbers for the orbitals, n, l, and m sub l. Size, shape, orientation. Each orbital has a unique set of n, l, and m sub l. We just said that there's a 4th quantum number that describes the electron. When an electron occupies an orbital, we make an attribution of the properties of the orbital to the electron. So we say the electron, we associate with that electron of a certain energy an n value, l value, and m sub l value, though we know those are properties of the orbital. And now that allows us to say that for each individual electron in an atom, there's a set of 4 quantum numbers that describe that electron. When we say that describe the electron, we mean that describe the energy of the electron, that tells us the energy of the electron. So 4 quantum numbers describe the electron. If 3 quantum numbers describe the orbital, the first 3 quantum numbers describe the orbitals, and the 4th one describe the electron, and the 4th one can have only 2 possible values, we can say that can be only 2 electrons in each individual orbital, or that the maximum occupancy of an orbital is 2 electrons. And we're going to introduce Pauli's exclusion principle, which essentially says that 2 electrons cannot have the same quantum numbers. Why is that? Because if 2 electrons had the identical same 4 quantum numbers, it would be like saying that there are 2 individuals in the universe who occupy the exact same volume in space, or they occupy the same space in the universe. If 2 people occupy the same space in the universe, it's because they are the same person. So if 2 electrons had the same 4 quantum numbers, they would be the same electron. And that tells us that 2 electrons cannot have the same 4 quantum numbers. So remember, orbitals are mathematical constructs. They are not real. We are using the model that, a hydrogen model that will only have 1 electron to simplify our understanding. And we will only briefly mention the multi-electron system. And for our discussion, we are going to make the assumption that all of the atoms that we're going to discuss have essentially the same orbitals as hydrogen. Why is this relevant? We always constantly ask ourselves, why are we learning this in this chemistry class? This is important because if we understand the energy of the electrons, the energy of the orbitals that they occupy, we know where they are in the atom, and we're going to be able to predict and explain their chemical behavior. So let's start populating the orbitals. We have our orbital diagram with some of the possible orbitals for hydrogen. Hydrogen has only 1 electron. Where would that electron go? It would go to the orbital with the lowest possible energy, or lowest orbital that is available and that has the lowest energy. Because in the universe, things tend to have the lowest, chemical systems, physical systems tend to have the lowest possible energy. Helium has 2 electrons. So where could that second electron go? Most probably it would not go up like to, let's say, 3D, because that's higher in energy than 2s or 1s. So that electron is going to occupy the lowest energy orbital that is available. Which one would that be? 1s, because we can accommodate 2 electrons per orbital. But now, since 2 electrons cannot have the exact same 4 quantum numbers, this second electron, since it is in the same orbital, would have the same values for n, l, and m sub l. So it has to have a different value for m sub s, for the spin quantum number, than the other electron. So one electron is pointing up and the other one is pointing down, and we say that the electrons are paired. Next element on the periodic table, lithium, has 3 electrons, 1, 2 in the 1s orbital. If we were to try adding that one electron, the third electron in the 1s orbital, it would necessarily have to have the same 4 quantum numbers as one of the 2 electrons that are already there. So that's not possible. So where does it go? It goes to 2s. Why doesn't it go to 3p? Because 3p is higher in energy, and the system will tend to have the lowest possible energy. And we keep going. Beryllium has 4 electrons. There's 1, 2, which pairs with 1. 2s, we have 1 pointing up, and the second will be pointing down. 4 electrons. We're missing an s there. Boron, 5 electrons, 1 up, 1 down, in the orbital 1s, 1 up, 1 down, orbital 2s, 1 up in the 2p. And you're asking, how do I know I place that electron in the far right orbital of the 2p subshell and not in the middle or the left? I say it backwards, but you get the idea. How do I know? We said that these three p orbitals are degenerate. That means they have exactly the same energy. So it doesn't really matter where I place it. I could just place that electron in the middle. The system would have the same energy because the 2p orbitals have the same energy. However, we are going to try to keep things straight and accommodate those electrons from left to right, just because we want to. Okay? Chemically would not make any difference. So what I just did was I described what we call the Aufbau principle. And the Aufbau principle, Aufbau, you will read, comes from the German word to build up or to construct, to build up. And we're building up the electron configuration of the atom. And just the same way that if you were building up a building, you would start by the first floor before you start working on floor number 8, right? And that reminds you of this idea that the electrons will occupy the lowest energy orbital that is available. Okay, that's the Aufbau principle. Now we have carbon 6. We have a carbon atom that has 6 electrons. So we have the 5 electrons for the previous atom. We're going to add another electron. Where will that electron go? I just said that the 3 2p orbitals are degenerate. They have the same energy. So you would be tempted to say that we can add that second electron to the 2p orbitals in any of the 3 orbitals here, right? One would be tempted to say that. However, there's a problem with that. Why? Because we already have 1 electron in this orbital, and remember that orbitals are volumes in space. And they're pointing in different directions. So they're separate and pointing in different directions. So if I were to place the second electron here, we may have a higher repulsion between the electrons. We're going to have 2 electrons occupying the same space. They're going to repel one another. Whereas if I have that second electron in a different degenerate orbital, they still have the same energy levels, but the electrons will not repel one another as much as they would if we place them in the same orbital. So that leads us to another rule, and this one's called Hund's rule, or Hund's rule, because it's German. And Hund in German means dog, D-O-G. But the reason why we call it Hund's rule is not because of the dog, it's because it just happened to be the last name of the scientist who proposed this idea. And what it says is that when we have degenerate orbitals, like in this case, the electrons are going to occupy them in such a way that we get the maximum number of unpaired electrons. They will be paired up here in the top example. They're unpaired down here. So we're going to get the maximum, the highest number of unpaired electrons when possible. Carbon atom, 6 electrons. What's next? Nitrogen. So where's that 7th electron going to go? It's going to go to the 3rd 2p orbital, so that we have the highest number of unpaired electrons. And you know what's coming next? Oxygen. We are going to add 1 more electron. Where will it go? It doesn't really matter, because at this point we can only place that 1 electron in such a way that it would be paired up with another electron, regardless of which 2p orbital we choose. Just to keep things organized, we're going to go from left to right, but it would be exactly the same if we had it in the middle or to the right. So we're building these electron configurations, and these are the things that we're bringing together. When we do so, we have to think that to get the configurations, we only show the orbitals that actually have electrons, occupied orbitals. We have to keep in mind Pauli exclusion principle, Hund's rule, the Aufbau principle, and understand what a ground state means versus an excited state. And all these ideas put together will give us a correct electron configuration, which will allow us to explain chemical reactions and predict chemical behavior. We're going to stop this video right here and continue shortly with another one.